Thanks for your introduction. I'm sorry that I changed my title, but I still focus on the unsupervised image denoising because I try to put our work in a more general framework and share my thoughts uh, by applying the deep learning techniques in image processing. Okay, here is my outline. First, I will introduce the modeling error when we want to reconstruct the image for the real applications. And I use real-world image denoising as a demonstration. And I will then extend our ideas for some challenging inverse problem like the seismic inversion. Okay, first of all, let's look at the imaging processing problem. Always we have observation data B, and the real imaging processing, we can imagine it as a highly nonlinear process, which means that we have fx equal to b, and we want to recover our true image x. And usually we want to simplify our analysis or simplify our computation, and we try to do some first order approximation of this imaging processing problem, like we simplify it as ax equal to b. However, we know that A is never perfect, and our data is always have noise. So which means that A contains some error and B contains some noise. As we know that if these errors and this noise can lead to severe artifacts in our restored image if we do not treat them carefully. Here, let me share with two examples. One is a blind image deblur, which means that we have one blur image and we don't know the blur kernel, which means that here we want to reconstruct our blur kernel and then we can do some inversion to get our clean image. So in the first step, usually we try to do some blur kernel estimation. If we have 2 pixels error in our blur kernel, and we will see that there are some severe artifacts in the restored image. Okay, this is one example when we have some error in our measurement operator. Okay, the other example is for the hyperspectral image denoising. In the hyperspectral image, we have many different bands, and the noise distribution in each band is different. And if we apply the row rank matrix factorizations to approximate this hyperspectral image, and we can simply apply the singular value decomposition method to restore this image. In fact, if we apply the SVD operations to the observation, we implicitly assume that the noise is Gaussian. However, in the applications, we will see that if we do the SVD decomposition, we will see many artifacts here, if we can see. Okay, so which means that we have to consider these errors when we want to restore the clean image. So this is the goal of our talk. Actually, we have considered this for some years from my PhD. First of all, we will treat this problem as a mathematical problem, which means that I want to add some analysis for these linear operators. The first thing I can do is that the analysis is a forward process, and I try to get some accurate description for this error propagation. And the other method probably is that if I cannot characterize the delta A, I can get some detailed description of the pattern of delta A, X on X. If I have this pattern, then we can apply the regularization method to extract these error patterns in our reconstruction algorithm. Actually, in fact, there are many other works for different applications. However, as we know that there are many deep learning methods applied for this image processing. So today we want to
we arrive at another problem is that can we integrate this classical approach and DNNs for modeling these errors in our image processing programs? In fact, we know there are many works along this direction. One is that we can enrolling some optimization problem algorithms, and we formulate it as a deep network, and then we can apply the end-to-end training to get this to get our results. The other method is that we can try to input our knowledge into the network architecture module design, which means that in the Professor Michael Bronstein's talk, we can apply some geometric knowledge in design when designing the modules in networks. Also, we can apply some knowledgeable laws in when we training the neural networks. So there are many attempts when we want to combine this model-driven and the data-driven approaches. So today I want to talk about my personal perspective along this direction is the AI-aided robust modeling, which means that let's analysis consider two advantage of these two approach. So first of all, the real data is always noise and inaccurate. However, when we direct apply the classical approach for this real data, the result is always terrible or unsatisfactory. However, when we have the enough training data, we can apply the DNN to get some promising results. But these DNNs are highly data dependent, unexplainable, and sensitive. So here, my goal is that can we combine the advantages of the classical approach and DNNs such that we can boosting the performance of classical approach. And also the classical approach can provide some diagnosis conditions when we want to change the DNN. So moreover, if we can have some mathematical theory, it could be better. But in this talk, I will don't talk about it. So here, my solution is that can we transform the data to meet the assumptions in classical models? Actually, in our classical model, we always have some assumptions related to our data or related to our mesh forward process. And when we want directly apply this classical approach to real data, the result is not good. This is because the real data, it does not meet the assumptions in our classical model. So if I can apply the deep neural network to the data such that the transformed data meets the assumptions in our classical models, in my opinion, it should be good if we can directly apply this classical model to the transformed data. Because in our classical approaches, we have some good theory such that we have some optimality conditions and explainable conditions when we deal with these problems. So today I will share with you a case study when we apply this concept to the real world image denoising problems. Okay, let's look at the noise denoising problem. This is a basic task in image processing. When we look at a typical imaging process, this is a typical process in a commercial camera. And in this part, we can see that there are many different kinds of noise when we get our image, such as there are some fixed pattern noise, shoe noise, or dark noise. And we know that this noise cannot be Gaussian. So if we directly apply the Gaussian denoising approach for these problems, it cannot be good. So this is our task. Let's revise the classical approach. when we do the classical modeling, we always have two terms. The first term is the data fidelity, which means that we want to measure the loss between the recovered true image and the observed image. And the second term is the regularization term, which we have so many good regularizations during the past 10 years or 20 years, like the sparse regularization or self-similarity regularization. And also we can have applied the latest learned regularization, which means that we can learn the prior when we want to restore our image. And the data fidelity term L always measures the uncertainty between the noise data and the true data. So this is my emphasis in this talk. And always we know that there are many deep learning approaches for doing the image denoising. And the most common approach is the supervised approach, which means that I have some training pairs. One is a noise image and the other a true image. And then I can train a neural network such that I can get a map between the noise image and the true image. However, in this approach, we know that the generalization error is a key issue. When the test image is out of the distribution of our training sets, then we can see that there are no denoising effects for the pre-trained image. So we always want to relax these constraints when we want to do the image denoising task. One approach is that I can relax the clean image to noise image. So which means that now I don't have the noise and clean image pairs. I have the noise and noise pairs. But these two noise images are independent observation of our ground truth. And they can show that under certain assumptions, and this loss is equivalent to the noise and clean image pairs. So this is a noise to noise approach, and they get a good result. And moreover, we want to relax this approach to the unsupervised setting. Here, I mean the unsupervised setting means that we don't have any pre-trained data set. We just train a network in a typical single image. So one promising approach is the deep image prior, which means that I use a network to represent the space of our image. And this shows some satisfactory performance for many inverse problems. However, as we know that here, the deep neural network have a good approximation ability. And when we train the network for a long time, it should have some overfitting issue, which means that here, the loss here is equal to 0. So it tends to overfitting. We have to do some early stopping. And the other approach is the so-called self-to-self approach, which means that in the single image process, I don't have the training pairs. However, I can use a random mask to construct many training pairs, many noise-to-noise training pairs. Because if I add the mask here, mi, and add the 1 minus mi as my target, then I can use this as my training pairs to train my neural network. And in our work, we want to combine the NN and the classical Gaussian denoise approach to deal with this case. This is because in a single image processing program, we don't have the training data. One approach is that we can construct many training samples by using random mask. And the other approach is that, in fact, when we do some classical modeling, we don't need training pairs. We just use one single image. We just use single image. So can we combine these two approaches such that I can make a meaningful loss? Then I can effectively combine the neural network training process and the denoising process in a single model. So this is a bit, I will talk about the details. So let's look at the state of one of the state of the art, the Gaussian denoiser, the so-called the BM3D. It actually consists of two stages. One is called the basic estimation, and the second step is the Wiener filtering. So actually, it is it finds a local similarity patch for one noise patch, and then use some averaging techniques such that we can achieve a good performance in Gaussian denoising task. However, this approach is not good for real-world image. Here is two example. One is from the Samsung smartphone, and one is from the Google smartphone. And here the left column are the clean image. The second column a noise image. And here we plot the noise distribution of these three patches. And the third column are the noise distributions. So here we can clearly find that this noise distribution does not uniform and does not satisfy the Gaussian distribution. If we directly apply the BM3D to this noise image, and we found that this image are not satisfactory or sometimes over smooth. So from this demo, we can see that the BM3D is not good because the real data does not meet the assumptions in BM3D. So one approach is that can we transform this data to meet the assumptions in BM3D? Actually, we have many approaches already. For example, we can use some mix of Gaussian to model this likelihood, or we can use some mix of exponential families to model this likelihood. And the other approach is we can use some VST transformations such that I want to find some transformations such as we can declarate the variance and the mean. And in that case, we know that the noise distribution can be treated as some more similar to the Gaussian distribution. However, both approaches have some fundamental issues when we do some real-world image. First of all, the noise is content and camera dependent. And in fact, we can not get the accurate noise distribution and or found these VST transformations in high dimension case. So here we want to use neural networks. So our idea is very, very simple. The first approach is, the first idea is that we want to map the noise image. Here, I have a noise image. I want to map this noise image into some latent space. And in this latent space, I assume that this latent image is a Gaussian perturbation of the true image. So which means that in this latent space, our latent image is an observation of true image corrupted by the Gaussian noise. And then I can apply the existing Gaussian denoiser to the latent image. So I can get the restored image. So the key component here is that if I can find a good map or a good neural network such that this assumption holds in latent space. So this is our key motivations. If we have these key motivations, then we can construct our model using our classical MAP language. So as we know that here the first term is the likelihood of our noise image. So in fact, in practice, we don't know the exact likelihood. So we can apply the variational inference such that I can get an approximation, which is called the abel of this likelihood. I think this is proposed in the variational autoencoder. Then if I can get some form of this able which is computable, then I can replace this MAP model by this new model. This is not accurate, but this provides a good approximation for our classical model. So under the standard settings in variational autoencoder, we can find that this able has some closed form. The first term is we call the data fidelity. The second term is a regularization. And we can apply some standard neural networks such that this G is encoder and this F is a decoder. In these assumptions, we know that the able has some closed form which can be input into our models or into our objectives. So finally, our model has this form. Here, the first two terms are the able of our term. And the last term is a regularization term. We can apply arbitrary regularization term in this framework. One way to solve this model is that we can apply the ADMM solver to solve it. In the ADMM solver, we know that they have 3 steps. The first step is we call the network training, which means that here we can train our networks, the encoder and the decoder. And the second step is that here we only left Y as a variable. So this is relaxed to the proximal operator of this regularization term. This proximal operator can be implemented by any existing Gaussian denoiser such that this regularization term is imposed implicitly. So, which means that in the second step, we can apply any existing Gaussian denoiser, like BM3D, like non-local mean, like wavelength-based or TV-based, any method. So this is our framework. And once I want to make one remark in our model, because in the unsupervised method, we always have some overfitting issue, like in the deep image prior, we have some overfitting issue. But similar happens in our model. Because our model has some trivial solutions. One trivial solution is that the encoder maps the noise image to a constant image, and the decoder maps a constant image to noise image, which means that if my encoder maps noise image to a constant image, and this I is a constant, so the last 2 terms must be 0. And if my decoder can apply a constant image to a noise image, so the first term is also 0. This is our trivial solution in this case. And however, we can show that if we use some common network architectures such that we use a convolution, pooling, or bilinear, or this upsampling components, this decoder cannot map a constant image to a noise image because it only maps a constant image to a constant image. So this is such that we do not have the overfitting issue in this sense. And then numerically, we can test that our average chaining loss is not equal to 0, which means that we always bigger than 0. So this means that we can expect that our model can converge to some meaningful solution. So this is our quantitative results. We have applied our method to 3 data sets, 2 CC and poly-U natural image, FMDD from microscopic image. So here's the non-local mean and the BM3D and DNCAN as our Gaussian denoiser. And we also compare our method with the VST plus the NLM or other Gaussian denoiser. And we can, from these results, we can see that our method actually boosts this classical method by a large margin. Okay, here are some visual results, and we can see some detailed comparisons. Okay. Due to the time limit, I think I should be accelerated. Okay, here is some latent space verification. As I mentioned before, our goal is to apply this neural network to a latent space such that the noise distribution is Gaussian. So here the last two columns are our transformed data, transformed noise by the neural networks. As we can see that it's not exactly Gaussian, but it's a value. We can see it calibrates the noise by a large amount. So we can expect we can have a good result by direct apply this classical model. And then we also apply our method to do some blend test. So this image are provided by the Huawei company, and here we compare with some existing deep network method and classical method. Okay. So here, let's do a quick summary. And in this work, we just have applied these ideas to the image denoising. Actually, we can extend this idea to some other cases. One is image segmentation, and we can do some unpaired training samples. So this is a natural extension. And today, I will still want to talk about some challenging inverse problems if we can apply these ideas, because as we can think that inverse problem all we have is real condition. If we transform our data to some cases such that this problem is good precondition, is good condition, so it's easier for any existing solver actually. So this means that the network actually looks like a precondition. So this is the second example. So let's do a quick revision for the seismic inversion. In seismic inversion, we will try to solve these least square problems. But this USM is our model. This model is the solution from this. We assume this is acoustic wave equation. And we want to do, usually we just do some gradient descent or use a joint state method to solve it. And in these applications, we know that the objective function value is always highly non-convex. And numerically, we know that there are many multiple local minimum existing. And in geophysics, they call this is a cycle splitting. And many efforts, we can do some global optimization, and we can also apply the latest over substance distance to a loss function and solve these problems. This is here our motivation is that if I consider this source term, we have a source term here, Fs. If we have some recurrent source, we know we have multiple local minimum. And if we transform our data to the Gaussian source, and we know there are only one minimum. So which means that in this case, when we use a recurrent source, we can transform the energy landscape from the non-convexity to a quasi-convexity in this case. So in general, we don't know the exact working mechanisms, but we hope this idea we can get a better solution or get a better conditional problems. So our model is here. We try to change our problems from the original problem to a new problem. In this new problem, we change the Fs to Fg, and this Dg is the observation data of this related to the source, And in this case, we hope that this inverse problem is better condition. Actually, we know that here we have two steps when we want to finish this task. The first step is that we try to simulate this DG under the assumptions of this FG, because in practice, we only have the DOBS and FS. So if we can write down its green functions, we know this is a deconvolution problem. We can use any existing deconvolution techniques to get this DG. Now here we try to use some deep learning approach, and we want to inference this DG by using the deep learning techniques, and we do not directly to solve this inverse problem, use end-to-end training. So we use some experiments on this Marmor's model. And our target here is we want to transform this weaker wavelets to the Gaussian wavelets. And the black part is our training data, and this red part is our test data. And we see that when this is the DOBS, this is our original observed data. And this DG is our transform data here. Okay, and we have two results. One is use the classical deconvolution results. One is to use the deep learning results. And we cannot see the difference, but if we see the residue, we have some difference here. When we use a basic approach, the error is much bigger than the deep learning results. And at the end, our goal is to do some inversion. We want to reconstruct our true image, or we want our true model here. So we have tested inversion performance. If we see the inversion, this is our initializations. The bottom is the result from the classical approach, which means that I directly solve the least square problem, use the adjoint state method. And these are results from our transform data. So the top one is the result from the deconvolution method, and the bottom one is from our deep learning method. So we can see a big difference here. When we directly, we can get a better conditioned problems, and we can apply a classical approach. We can actually also get some satisfactory results. So let's quick summary my talk here. And I want to show that we have two tasks here: image noising and seismic inversions. And we have two steps we want to emphasize here. One is to do the data transformation by DNN. And we don't want to do the map directly between the data and the model. We want to directly apply this deep neural network to the data, not related to model. And then we apply the classical method to the transform data. So this, I want to show this results. And also, if we consider this part, we have many other things should be considered in future, because we use deep neural network. So the robustness of this deep neural network should be considered. And we have many work. There are many works along these directions, like the adversary robustness. And we also want to have some training algorithm for this DNN, because if I want to get this the reliable transformation, we have to find some training algorithm that should be suitable for the inverse problems, not for the forward problem. Not only, and we can have some approximations for this data representation whenever we use dynamic model or we use some optimization models, whatever models. Okay, here is my talk, and all the paper and the code can be downloaded from my homepage. Thank you.